Done with Ilaria Manetto. She's a professor at the University of Genova, and unfortunately she couldn't come today, so she asked me to deliver the talk instead of her. So what I will present is a theoretical model we are formulating to derive energy release rate and mode mixity phase angle in the inverted four-point bending specimen, which is a fracture mechanic test which has been recently proposed and applied to measure the interfacial toughness in thermal barrier coatings. And I'll show you our model. I'll start with an introduction, I'll show you our mechanical model, and then show you some results. So thermal barrier coatings are used in order to protect and reduce the temperature of the underlying alloy metals, metal alloys, in aircraft and power generating turbines. And they're essentially a layered system with three layers. So we have the metal substrate, then we have the metal bond coat, which is usually very thin, and then we have the ceramic top coat. And among the dominant failure mode is the failure mode by spallation, which is driven by interfacial delamination. And interfacial delamination typically grows between the three layers and under mixed mode condition, and usually with a large component of mode 2. Now, the inverted four-point bending test is a modification of the well-known four-point bending test, which was developed by Lambides at Santa Barbara many years ago to measure interfacial fracture toughness in layered system. And in this test, loads are applied this way in order to create a state of pure bending in the intact part of the specimen and in the lower delaminated arm, while the upper arm is essentially stress-free. And the delamination in the specimen grows under steady-state condition, and the energy release rate and the mode mixity angle can be defined very easily with any methods. We applied Sue and Hutchinson method, and they are shown here, so they do not depend on the crack length, and the mode mixity angle is around 41 degrees. So this specimen has nearly an equal mix of mode 1 and mode 2. It has been applied to thermal barrier coating, but as I said, thermal delamination typically grow with a much larger mode 2 component, so it's not useful to define the fracture toughness under those conditions. So the inverted four-point bending test was suggested in a paper by Hutchinson and Hutchinson in 2011. And recently, it has been applied to thermal barrier coating by Vanois, a group of French researchers. And they performed experimental tests, and they also conducted finite element analysis. Now, the idea is very simple. The loads are simply inverted in sign. And therefore, we still have a constant bending moment in the intact part of the specimen, but now the crack faces come into contact at the midspan. And from the finite element result, they observed that contact occur only at the midspan, while the crack surfaces are open over most of the length of the crack. And Sue and Hutchinson and Hutchinson in 2011 obtained an analytical solution for the energy release rate and the mode mixity angle. And that solution was obtained based on a number of simplifying assumptions. They assumed the specimen to be homogeneous. They neglected shear deformation. They neglected near-tip deformation, so they assumed the delaminated arms to be clamped in at the crack tip cross-section. And they also assumed frictionless contact, so they neglected friction in the solution. Now, based on this, they calculated the transverse displacement at the midspan, and imposing a compatibility condition on the transverse displacement of the two delaminated arms, they obtained the contact force. And then by applying classical method, they defined the energy release rate and the mode mixity angle. And this solution is again a steady-state solution. Energy release rate and mode mixity angle are independent of the crack length. And the mode mixity angle is around 60 degrees, minus 60 degrees. So you see that the mode 2 component is much larger than the mode 2 component in the regular four-point bending test. They also performed some finite element calculation, and here you see the normalized energy release rate and the mode mixity angle as function of the length of the crack. And the different curves correspond to different value. They treated the problem assuming Coulomb friction, and they consider different value of the friction coefficient. And what you can see from this diagram is that it's true that the steady-state limiting solution are approached, but these occur only for very long crack, while the solution for short and intermediate crack strongly depend on the friction acting at the point of contact, and the solution are also affected, as you can see, they differ from the steady-state solution. So our idea is to formulate a mechanical model for this specimen which account for all the effects that were neglected in the original solution. So we want to account for friction effects on the fracture parameter. We want to account for shear deformations, which are important when we are dealing with short cracks. And we want to account for the near-tip deformations, which are important not only for short crack, but also for intermediate crack lengths. So the aim is to obtain a calibration formula for the inverted four-point bending specimen, which is valid for intermediate crack lengths. And this formula, as you will see, will allow us to understand behavior, to explain the experimental and the numerical results. And also, it will allow us to define the range of applicability of the steady-state limiting solution in order to design the experimental test in the lab so that the steady-state condition can indeed be approached in the specimen. So regarding friction, we account for friction using structural mechanics approximation. So essentially, we consider Coulomb friction, and these two frictional forces are then transferred to the neutral axis of the beam, and plus the compensating moment. And what we found out is that the effect of friction is minimal on the contact force, while friction does have a very important effect on the fracture parameters, as we already noticed in Hutchinson results. For shear, we simply use the theory of a shear deformable beam to solve the problem. And for the near-tip deformation, we decide to use the concept of root rotations and root displacement. So what are the root rotation and root displacement? Root rotation are essentially relative rotations of the crack tip cross-section of the different arms of the specimen. And this relative rotation arises due to the compliance of the material ahead of the crack tip. And if the crack is long enough, they can be defined as a linear function of the crack tip forces, moment and force resultant, through some compliance coefficient. And the value of the compliance coefficient can be found in many papers in the literature, both numerical solution and recently also analytical solution by Konstantin Ustinov. The root displacement are a similar concept. So it's a relative displacement between the axis of the delaminated arm. And this is a concept which has been recently used by Towles in a very nice paper where he compared different solutions for the double cantilever beam specimen. Now, this is an important idea of our model, so I want to tell you a little bit more on this root rotation and root displacement coefficient. And to explain why they are useful, I will refer to the double cantilever beam test. The double cantilever beam test is a well-known test. Here you see a symmetric double cantilever beam, and I'm also assuming homogeneous and isotropic material. So this is the expression of the energy release rate for the double cantilever beam, homogeneous and isotropic. You probably have seen this expression. And you can see that here in bracket we have this term which is squared. Now, if we apply the J integral and we introduce shear deformation, root rotation, and root displacement coefficient in our solution, we can explain this term and separate all the different contributions. So the first important contribution is bending of the delaminated arms, and this is the dominant contribution. It goes with the length, crack length square. But then we have a contribution from shear deformation along the beam, and then we have two additional contributions which are due to this localized root rotations. And we have root rotation produced by the bending moment at the crack tip and root rotation produced by the shear forces at the crack tip. And this coefficient, as I said, can be found in the literature. They've been tabulated for different material systems and different position of the crack. So we can now use them with confidence. And as I said, they've also been verified analytically recently by Konstantin Ustinov. We can also use a different approach to calculate the energy release rate. We can use the compliance method. And the compliance is the transverse displacement here due to a unit load. If you apply the compliance method to define G, then we can separate again all the different contributions, and we will see the effect also of the root displacement, which need to be taken into account in the solution if we use this method. And this coefficient, they cannot be found in the literature, so what we did to calculate the root displacement was to assume that this material here can be treated as a shear deformable beam on a Winkler foundation. And by doing that, we were able to obtain this compliance coefficient. So we decided to apply this approach to our inverted 4-point bending test. So we calculated the transverse displacement at the midspan of the delaminated arms using shear deformation, root rotation, and root displacement. We then apply a compatibility condition of the displacement in order to define the contact force. And the contact force will depend on the applied load, the geometry, and on these root rotation and root displacement coefficient, which we know. Obviously, when the crack is long enough, we will approach the steady-state limiting solution already defined by Hutchinson and Hutchinson. And here you see our contact force as function of the normalized crack length. The black curve is the solution of the model, and the red curve is the steady-state limiting solution. You can see that we are approaching the steady-state limiting solution, and which is approached only for very long crack length. The boxes here are 2D finite element calculations that we performed, and you can see that the model very well described the 2D solution, but for this region, with the boxes in red, and this is where we observed that for very short cracks, the assumption of point contact at the midspan was not valid anymore, because contact occurred over a much extended region. Then we can apply technique to calculate the energy release rate. What we did, we applied the methodology originally proposed by Sue and Hutchinson that was modified by Towles and by Andrews and myself to account also for the presence of shear. And we were able to define this analytical expression for the energy release rate, which depend on the applied loading, on the contact force, on the geometry, and on all the compliance coefficient for root rotation and root displacement. And again, when the crack is long enough, we are approaching the steady-state limiting solution. So let me show you this diagram, which is my last diagram. This is the energy release rate normalized to the steady-state limiting solution as function of the crack length. The steady-state limit is in red, and these curves, the black curves, are the solution of our model, and they correspond to 3 different friction coefficients, Coulomb friction, 0, 0.25, and 0.5. And the results are compared with the finite element result in the original paper by Hutchinson and Hutchinson, and you can see how well our model is able to reproduce the behavior in the, for crack length, which are intermediate. You can also see by looking at this diagram that the steady-state limiting solution is approached only for very long crack length, and therefore the idea is that you can use this theoretical model in order to define the proper geometry to use in the lab if you want to propagate the crack under steady-state condition. We also obtained some result for the phase angle, but I think due to the lack of time and the fact that we are still not sure about those results, I just go to my conclusions. So we formulated a mathematical model for the inverted 4-point bending test, and the idea is to account for shear deformation, for root rotation and root displacement, which describe the near tip deformation ahead of the crack tip. We account for friction at the contact point, We noticed that for long crack, the fracture parameter indeed approach the steady state limiting solution, but for shorter intermediate cracks, the effect of near-tip deformation and friction are very important. The model can be used to understand the behaviors, to explain experimental and numerical results, and to define the range of applicability of the steady state solution. So I thank you for your attention.